All right, let's get into it. If you're gearing up for your GCSE computer science exam, you know that algorithms are a massive topic. Today, we're going to break down the 5 essential searching and sorting algorithms that you absolutely have to know. Let's do this.
So think about it for a second. How would you actually do this? Would you seriously start at the A's and read every single name until you find the one you want? Of course not. You'd use the fact that it's in alphabetical order to jump right to the correct section. This right here is the core problem that searching algorithms are built to solve.
So, here's our game plan. We'll kick things off with what the exam board actually expects from you. Then we'll dive into the 2 types of searches and the 3 sorting methods. After that, and this is super important, we'll look at what examiners are looking for, and we'll finish up with the key takeaways for your revision.
Okay, let's get really specific here, because this is important. Everything we're talking about today comes directly from the OCR J277 specification, specifically section 2.1.3. So this isn't just some random computer science chat, this is targeted exam-focused revision. Our whole mission today is to make sure you can walk into that exam feeling totally confident about these 5 algorithms. We're not going to just memorize facts, we're going to focus on understanding how they work and, just as importantly, why they matter. That's what's going to get you the marks.
So, you've got a mountain of data. How do you find that one specific thing you're looking for? Well, the first and most basic way is something called a linear search.
A linear search is, well, it's pretty much exactly what it sounds like. You go in a straight line. You start with the very first item and you ask, is this what I'm looking for? If it's not, you move to the next one, and the next, and the next. That messy shelf analogy is just perfect because a linear search doesn't care one bit if the list is sorted or a total jumble.
Let's actually watch it in action. Say we're looking for the number 15 in this list. We start at 4. Nope. Then 29. Nope. Then 8. And we literally check every single item in order until, bam, we hit our target. It's super simple to understand, but you can probably already see how painfully slow this would be if you had a list with, say, 1 million items.
And that brings us to a much smarter way of doing things, the binary search. But, and you've got to remember this, it has one absolutely critical rule. The list must be sorted first. This thing works by repeatedly chopping the problem in half. It's a classic strategy called divide and conquer.
So, how does it work? It's genius, really. You jump straight to the middle of the sorted list. Then you ask, is the number I'm looking for bigger or smaller than this middle one? If it's smaller, you can instantly throw away the entire second half of the list. You just got rid of half your problem in one step. Then you just repeat that process, having your search area every single time until you find what you're looking for. It's incredibly fast.
Okay, so let's put these two head to head. It's really important to understand their key strengths and weaknesses.
So here's the big trade-off. Linear search is slow, but it's flexible. It'll work on any old list, sorted or not. Binary search, on the other hand, is lightning fast on big lists, but it has that one non-negotiable demand. The list must be sorted. And let me tell you, that prerequisite is a favorite thing for examiners to ask about, so burn that into your brain.
Which, leads us perfectly to our next question. If a binary search is so great but needs a sorted list, how do we get a sorted list in the first place? Well, that's where our sorting algorithms come in, and you need to know 3 of them.
First up, we have bubble sort. It's one of the simplest to get your head around. It just goes through the list again and again, comparing items that are right next to each other. If a pair is in the wrong order, it swaps them. It just keeps doing this over and over until it can go through the entire list without making a single swap.
You can see it happening right here. With each full pass through the list, the biggest unsorted numbers kind of bubble up towards their correct spot at the end. It's easy to understand for sure, but just like the linear search, it's not very efficient for big datasets.
All right, next up, insertion sort. Now, the absolute best way to picture this one is to think about sorting a hand of playing cards. As you get each new card, you don't just stick it on the end, you slide it into the correct position among the cards you're already holding. So here's the process. You basically imagine the list is in 2 parts, a sorted part at the beginning and an unsorted part at the end. You take the first item from the unsorted section, figure out where it belongs in the sorted section, and insert it there. You just keep doing that until there's nothing left in the unsorted part. And that brings us to our final sort, merge sort. This one is a real powerhouse. It uses that same awesome divide and conquer idea we saw in binary search, which makes it super efficient, especially for large lists. It's also known as a stable sort, which is a fancy way of saying if 2 items are equal, it keeps them in their original order. That's actually a really big deal in real-world applications, like databases.
So it works in two main stages. First, you divide. You just keep splitting the list in half and in half again and again until all you have are a bunch of tiny lists with only one item in each. And a list with one item is, by definition, already sorted, right? Then comes the conquer part. You start merging these little lists back together in pairs, putting them in the correct order as you go until you're left with one single perfectly sorted list.
Okay, deep breaths. This is probably the most important part of this whole session. Let's cut right through all the noise and look at exactly what the OCR J277 spec says you need to know and what you don't.
This is it, folks. This is your revision checklist, pulled right from the source. Notice the words it uses. You need to understand the steps. You need to be able to apply the algorithm, meaning they could give you a list of numbers and ask you to show the steps, and you need to be able to identify one. So you might see some code and have to say, that's a bubble sort because I see it comparing adjacent pairs inside a loop. And now for the best news you're going to hear all day, I promise. The specification explicitly says you are not required to memorize the code for these. Do not waste your precious revision time trying to learn lines and lines of code by heart. Focus on the process, the logic, the how, and the why. That is what gets you the marks.
All right, let's bring it all home. When you're in that final push for revision on this topic, what are the absolute key things you need to focus on?
It really just boils down to one number, 5. That's it. 2 searches, linear and binary, 3 sorts, bubble, insertion, and merge. If you can explain how each one works, talk about its pros and cons, and remember any special requirements, like binary search needing a sorted list, you are in a fantastic position for your exam.
So, I'm going to leave you with an exam-style question to get you thinking. Imagine a high score table in a game. It's already sorted, but a new player just got a new high score. Which sorting algorithm would be the most efficient to just slot that new score into the right place, and why? Having a good answer to that will prove you've really understood these concepts. Good luck with the revision!